Okay, hello everybody. You are, thank you, Godwin. Thank you, Andrew.
As I slightly misspelled slides, okay, I'm here to talk about building a hosting platform with Python. Quickly introducing myself, I'm Andrew Godwin. I'm a long-time Python developer. I've been developing Python for around 5 or 6 years now. I'm a general core committer as of last year, and I'm also the co-founder of EuroPython, which is, I see on my t-shirt, that is a question. So, as a brief background, EuroPython, or EPIO, or how you pronounce it, is what's called a platform as a service. Essentially, it's a way of running hosted Python code and potentially other ones in the future. We handle the systems administration, we handle some of the databases, we handle load balancing, we handle backups. It's very much getting together your code and go. For those who are in the Google App Engine, it's somewhat similar to that. So, basically, describing why I'm here to give you, first of all, an overview of our architecture, roughly how what we do works, the different components involved, different servers, some of the basic challenges we face. And then I'm going to go through sort of what we use on technology stack and why we use it. And we go through our experiences with certain libraries, why some things are good, why some things are bad, and why we just moved away from using certain other pieces of software. And finally, I'm going to give you sort of a few insights in how we've learned over the last 6 or 7 months as we've built this, what we've learned so far, what's potentially ahead in the future, and general good advice for this kind of scenario. So first of all, our architecture. In terms of hardware, we have various sort of hardware. We have real, proper sort of servers that go to racks. We have Linux machines, and we have EC2 machines as well. These will vary in their cost, in their performance, in their disk I/O, in how reliable they are, and also to add to the mix, we also support both IPv4 and IPv6. So it's a very sort of heterogeneous mix of things there. And also the network. We run stuff in the UK, in London. We run stuff in the US, in Amazon's North Virginia place. The latency between those two can vary. It's often 90 milliseconds. It can go up to 200 or 300 milliseconds. So you've got, in sort of computing terms, a very large amount of time delay there. We also have internal network issues. In our own data center, it's very quick. You're sub-millisecond most of the time. In Amazon EC2, we've seen internal latencies of up to 20 seconds sometimes, so you really got to be prepared for a very wide range of scenarios. We also have lots of very small components. Our philosophy is to build things small and build lots of them. That way, one thing fails, it doesn't sort of take anything else with it. So, as of last night, when I finished this slide off, we have 17 different daemons running on a variety of different servers. And all of these daemons need to communicate with each other, they need to swap state. There's more than one of most of them as well, so it's quite a complex system. And also, being a hosting company, our main task is to keep everything running all the time. It's very important that not even one of our subs dies, because it's bad for us, it's bad for the person in question, and it's just not a good place to go. That means that everything in our architecture is tied to run in pairs. Wherever something there is, the idea is that it can fail. We're not quite there yet, but we're very, very close. We also need both high availability, which means that should something die, it switches over, and backups in case you delete a file or something gets in and deletes things, or there's a vulnerability to the following morning. High availability, like for example, database replication, is not backups. Don't rely on them. If something goes in and deletes some rows, it'll happily replicate it to your slave, and you're lost all later. Another interesting thing is because of our distributed nature across sort of various geographical locations, the idea of centralized state is very hard to keep. You have some centralized state, but it's very, very expensive whenever you query it, and especially when you update it. So we try and run as little centralized state as possible. Another big thing for us is security. We run everything on the same box. One virtual machine per site would be too much overhead for us. And a lot of the sites we run very small, they don't get very many hits. And having extra overhead in the kernel or the virtualization layer, slowing it down around disk layer access, means that that's just not feasible. So, first of all, we have that problem where we've got perhaps 50 to 100 apps, all on the same machine, all under the same kernel, all running at once. Also, some of our own code runs as root for obvious management reasons. You can't do certain things with different processes and forking without doing that. So we've got to make sure what we write is very secure. So we have a combination of daemons running as root, programs running with lower privileges, and also very strict permissions, CH routing, and various other isolation options that the Linux kernel uses. A lot of those have been there for projects like OpenVZ, so it's very much sort of close to virtualization level of isolation. The other problem is that even Python sites are pretty varied. As well as Django, you've got Flask, you've got Bottle, you've got Zope, you've got all these kind of different ones as well. There's many more frameworks, as I'm sure many of you know. And so, as well as supporting all those, we support other languages in the future. We can't rely on just Python, in the long term. So we've got to have this very flexible system that is both easy to use, but also can accommodate a lot of different things. There are a few things like which database we choose that we have to decide ahead and be less flexible on. For example, when you say you use Postgres, you don't use MySQL. That's more because maintaining two whole database clusters of different technologies is too much work for us right now. We can add them in the future. So the main crux of this talk is what do we use and why do we use it? The basic technologies here are eventlets, 0MQ, and Postgres. Now, most of you know about how Postgres works, so I'll focus on the other two, most of all. Historically, we also did a lot of things in Redis, which since moved away, but I'll talk about in a second. And we also use a lot of Ubuntu, Debian, packaging, tools, processes, that kind of thing. Combined with Puppet to do a lot of our deployments. Moving for data between our daemons, we have two kinds of data. There's message passing, which what most of the system runs off. This used to run through Redis, but now runs through 0MQ. Essentially, whenever there's a state change, whenever an event occurs, whenever you want to reflect something, there's usually a message, sort of request response, or some kind of push cycle. There's also stored state, things like application permissions and things like that. They're stored in a centralized Postgres, or if it's logged into plain text files on disk, because they're better than Postgres, that kind of stuff. In terms of storage, we have two different kinds of storage. We store access disk images, which are sort of 20 to 50 megabyte chunks of files. They work very well on cluster-FS, where your overheads are very low compared to the file size. And we also store lots of small files, things like perhaps uploaded images or like caching or thumbnail directories. Those are a lot harder because we're investigating those. What we're looking is using ButterFS, cluster-FS, those kind of things. The problem, especially with ButterFS, is that they're very much still in development. ButterFS in particular doesn't even have FSCK yet, as far as I'm aware, so yeah, you've got to tread lightly with these things. So Reinvent is a shiny code team for the future. If you've been to Geovent talk as well as previously, you get the idea. It's the idea of green, that's the idea of filling in very much like Reinvent. For those who aren't familiar, Reinvent is a way of doing parallel processing in Python without using threads and without using processes. Essentially, it's based on Greenlet, which is a very small module that plugs into the Python interpreter that enables very lightweight threads that literally just has sort of a stack and nothing else. You can run literally millions of them on a single process. I've tested at least 10 million at once, and they all got stinks and they're all fine. It runs on multiple backends. You can run a little event, like Gmail does. You can run ePoll, you can run Select, and a variety of different things. It's very compatible. And the idea is that you write the programs as normal functions, but then you have certain functions or certain operations that yield control. As from the thread control, from the thread perspective, it's seamless, it's transparent, you don't see any change. Unlike, let's say, Twistedly, you can go deferred back and go attach callbacks. As an example, this is a very brief example of Redis. What I've got here is a simple thing that goes over 10 URLs and fetches them. It's what Redis was originally built for, and certainly what people use it for. We have one function, it's a normal function, it takes a URL, and just calls URL open. The key difference is at the top, we've imported URL lib from event.green. That means we have the asynchronous version of URL lib. And that means that this call will block the calling green thread until it gets the result back from the server, and then it will return it. That then means that we can spawn 10 of them at once, just run them all, they're all going parallel, and then when they get the results, this function will resume, assign it to this array, and then the function will exit. This is a very, very simplified example. The key feature here with things like Redundant is that it seamlessly sort of interoperates with any other library that's expecting sort of normal threads of behavior. You can also monkey patch the Python standard library in Redundant. So things like socket, things like URL, all the normal imports. Imagine you get the right asynchronous versions. We try and tend away from that because I don't like monkey patching, but it is possible. So we've built up a sort of standard way of using eventless internally to try and make some kind of sanity out of this. As I said, most of them are as daemons, so we have standard eventlet-based daemon sort of framework. It has multiple main loops, each one's a green thread, and if any of those die, the entire process quits. We believe in failing hard. If something goes wrong, we fail our process completely hard, and then the monitoring sort of upstart on that box comes in, takes over, restarts the process and logs errors, so we see what's going on. We also log both to standard output, or standard error, and also to remote syslog, so you can have centralized place for all logs. Our daemons look something like this. We have a core-based daemon class, and then you just subclass it, specify your main loops, and then you have a little pre-run hook there where you can do some assign some basic initial stuff. If not, that one's got in it for flexibility reasons. And then we have decorators, like resilient loop. This says, run this loop, split a second between iterations, and catch any trace backs. And so, literally, this loop here, every second, it sends a heartbeat to one of our, what we call, nexuses, and says, how I'm here, I give you this service. Greenlit in particular can be interesting. You've got to use Greenlit-friendly libraries with eventlet. Other libraries will work fine, but they'll block the entire process, because any blocking call in a green thread blocks everything. Green threads aren't in parallel processes, they're just very, very fast switching. That's what their code is. If you are in a green thread and you just do a very low like, if you time.sleep, for example, that will just block. It's your responsibility to get in the green thread, do something very quickly, and then quickly call a synchronous function or that exit. Otherwise, you're going to start slowing things down. Luckily, Redundancy has very good support for a lot of standard libraries and the standard loop. It supports, as I said, URL loop. It has Postgres support as well. It supports Zero and Q, which one we'll be using it, and a variety of other things, all in that eventlet.green package. So you can just go in there, import the library you want, and then use it in that monkey patching. And again, if you've got other libraries or frameworks like Django that don't support eventlet natively, we can monkey patch that support in, and it generally works quite well. There are still problems. So you can still have race conditions, even though it's a single thread at a time, because if you don't quite work out where those context switching points are, you can be a bit lax and have sort of, say, one dictionary assigned while another one's waiting. As I said, ungreen modules block everything. You've got to be very careful about that kind of thing. And also, some combinations of libraries and situations have very odd bugs. For example, if you have an unpatched Django and a patched Cyclic VD2, you will occasionally get massive hangs because Django tries in the same direction twice with different green threads and this just doesn't like it. So in that case, we have patched Django to realise it needs to make a new connection for every green thread. That's an annoying bug. Still, as I say, it's very, very useful. We've had upwards of 10,000 threads running in production, all doing useful work. Most of it, of course, is I/O rate because we've got a lot of networking, but still, keeping how much data at once is very handy for us. Multiprocessing, for example, falls over. You can't have 10,000 processes running at once in any kind of sensible form or any kind of sensible size box. And also, you can then have threading modules that make things a lot easier. In threading, you can lose control of the thread at any time in the middle of an assignment, for example. Eventlet guarantees you that you only lose control at points where the functions you call are defined to be Greenlit compatible. So you can actually do a whole set of array assignments and then call a socket function, and you know that this section is going to be safe. There's also things like locks you can have and timeouts that you can use with statements, so you can guarantee that. Redis. Now, Redis is what was arguably born on. It's the main thrust of us at the time. For those who aren't familiar with Redis, I'm going to say it's a key value store with extra bits. In particular, the values can be strings, they can be sets, they can be lists, they can be hashes. It has messaging support, and publish, subscribe, all that kind of thing. It's an amazing little database. And at the beginning, I'm talking sort of like December last year, we put everything in Redis. This includes the 20 megabyte disk images. They went to Redis. It was a massive store for everything you put in there. We quickly moved the disk images to disk because it turns out storing 20 megabytes in a database is not a good idea. And a lot of other things have moved out since. In February and March, we looked at what we were doing, and as we evolved, we realized we were doing a lot of filtering queries, i.e. going to reset keys, looking at values, and basically doing a where clause. So we moved all those things like user information, permissions into Postgres, which is clearly a lot better at filtering and selecting things. And we left things like messaging and the app information in Redis. And then very recently, we moved everything out of Redis now. The app info moved to Postgres as well, and then we moved the messaging to zero key, which I'll come to very shortly. And so this means that alas, Redis is no longer part of our backend. But it's not really because it's bad, it's not right for us. I've used Redis very successfully for other projects in the past. I wouldn't recommend it as a code data store. As a working set for doing complex operations like set union, it supports that natively. It's very good. And once we start getting sort of the limits of relational database constraints and stuff, we may revisit Redis as a way of sort of doing caching and sort of trying to denormalize some of our data. I mean, in particular, what's very exciting is something called Redis cluster, which is still in the works and happening for a while. It's meant to be a sort of more sensible distributed key value store, a bit like Lasagne, but more sane. So, zero key. Now, it's mentioned briefly this morning, but for those who aren't familiar, zero queue is not a message queue. There's no server like backend queue involved. It is a high-level socket abstraction. You make sockets, you tell them endpoints, and that's how it works. The bonus is it comes in many different sort of flavors of different types. It has pub/sub, which is a lossy but broadcast-based socket. It has rep, which is this one here, which is a request-reply format, so it enforces you just sort of like from repeated calls and things. Push-pull, which is a one-directional socket, used for like pushing logs or pushing statistics. Xrep, this one, which is an extended version of the request response where you can do multiple things at once. And also a special one called pair that you probably shouldn't use. A brief example of zero queue, you make the context, which is basically a sort of zero key for this process. You then make a socket. In this case, I'm making a request socket. You can connect it to multiple endpoints. Zero queue doesn't care. You can give it as many endpoints as you like, and it will load balance correctly across all of them. This is why we use it. It really makes the balance system a lot easier. So in this case, my requests can go to one of these two servers. Zero queue will try both of them. If one of them's down, it doesn't care. And both down, just wait until one of them reappears. I just do soft.send. I send a packet, which is always a string, and I just receive the packet again. It's basically only based on string based. There's no nasty encapsulation, and it's very, very simple. We mostly use it with the request response pattern. We have a custom decorator that runs multiple sort of receive requests in different green threads for each request, and we wrap the packets in JSON. We encapsulate packets as JSON, and then also have security measures like signing, because obviously we're on an untrusted network. It's the internet. An example of our loop. This is sort of like the daemon you saw earlier, except now we have these ZNQ loop decorators, and all they do is they open the socket on that port, which is defined up here by the attributes, and then for every request they get on that port, they just call the underlying function once. So here you can see if there's a request, it just returns an error, so a slide demo, and then this pull one, you just take data and just print it to the console. Obviously our real ones are a little more complicated, but it makes programming in this way a lot easier. There are many, many nice things about zero queue. Event has very good support for it. This is reasonably recent in the last 2 releases, but you can now use Eventlet and zero queue and any Eventlet hub. It just works. We've not found that very bugs with it at all. Zero queue itself can use TCP as a transport. It can use PGM, which is a multicast transport. It can use in-process communication, which is between different threads, if you're sort of writing C. It also supports a few other sort of slightly esoteric forms of communication. It is allegedly faster than the raw messages on TCP over TCP, purely because it avoids things like if you're technical slow start, and it does batching to make sure that it fills up entire packets. And also, it doesn't care about state. If the other end's down, we'll just wait. If the other end's busy, we'll just wait. If your network's down, we'll just wait, and it will then get there in the end. And it's a nice way of not having to worry about the whole dance of bring up server 1 first, then server 2, check they're connected. If a server dies in the middle, it will just wait for it to reboot and can't again, or just, if if one of our 2 servers died, it will just send a request to the other one instead, and it all stays up. So that for us is very convenient. Procedure terminals. So we run a lot of commands, and for those who aren't familiar, commands usually have to run in pseudo-terminals. Now, back in the long old days of Unix, there were things called real terminals, which was sort of bloody glowy 80 byte, vertically, but they were proper control terminals, and then people realised they had network access. And so, if you want to interactively sort of play with applications commands remotely, you need a pseudo terminal. SSH is what it uses to give you a proper shell. And so we need them. The only problem with them is that they're kind of archaic. So our first attempt was to just run processes and sub-processes. Don't care about inter-identity, feed it some standard input, wait for it a little bit, and then read the sound out again. This was great, it worked flawlessly, but you couldn't interact with them. Things like Django that ask you for passwords when you make a database, that wasn't going to work for us. So attempt 2. Python has a PTY module, it has many very fun modules that we'll see later. So we took that, we looked at the documentation, we used raw OS file handles right down to the sort of the Unix level. So, okay, right, we'll try and make it really compatible. And it worked initially, it was really good. And then we started seeing errors on a high level. In particular, it started confusing file handles and started writing PTYs to the logging, logs went to the PTYs, some of the sockets kind of went to the wrong place as well. And it turned out we were somewhere, we were leaking file handles in a way that they start writing to the wrong places. As an example of how horrible this code will be, I've got 2 snippets. This is actually what we usually see as something like sub-process. This is how you spawn a sensible sub-process in Python. In particular, we're going to import the garbage collector and disable it first. We've got some nasty provisions in there. You then fork using the PTY fork. If it fails, you're going to re-enable the garbage collector. If fork comes back to 0, then you're the child, you run the program, excellent, that's all good. Otherwise, you in the garbage collector and use some nasty things. Use FNCTL, which you should never, ever have to use, to make it non-blocking. You have to make 2 different threads, input and output. You have to then wait on it in a non-busy loop, and then kill the threads in the right order so they don't block, because if you block them wrong, they'll just won't do anything. And then we have to close it. And somewhere in here, there's a brace condition. I worked for several weeks trying to find it. Unfortunately, I never did. So in the end, we went the sensible way and used sub-process with a wrapper. The wrapper merely takes a PTY, puts it on standard input and standard output. It's much more reliable. It uses built-in Python file handling, and if it leaks, it leaks as one process and that's it. So in the end, the simplest thing here works. I also want to go through a few of the other Lasagne modules in Python that we use for various different things, just to give you an example of what's in there. So the resource module. Those of you who have done any kind of high-level programming will run into the problem of running out of file handles. You always get it, so like, you start doing really well, you get just over 1,000 users, and then bang, you run into a file handler. The resource module exposes the low-level calls in the sort of C API that lets you set those in process rather than using like unit or potential security and things. And also lets you discover limits. So all our demons that use on file handles, like a load balancer, uses a module to query up the number of file handles, try and increase them, and basically just quick interrogating to make sure they're capable of running sensibly. If they can't, they'll just exit. And then we get lots of errors and go, oh, and then we're going to fix it. The signal module, again, many people don't use this. If you're writing any kind of daemon, any kind of process, you really want to import signal and start catching the right signals. In particular, signal 15, SIGTERM, you want to catch because that will get you control Cs. So we catch those. They're both from the keyboard and from a monitoring thing if you're trying to restart the daemon to make sure we can exit cleanly and know about the right thing. We also do other signals. For example, Unicorn listens to a few of the high-level signals, like C-user1, I think, to make sure to have to reload things and various other daemons as well. Generally, use them for like reload configuration, kill yourself, that kind of thing. But knowing that you can use those is kind of important. As exit really is kind of useless as well, I can tell. It lets you run a function as exit, if you exit cleanly. So it's basically the same as putting the code in the bottom of your main loop. We just use this in our command line client for read line support. I can see it being useful if you're a library, you need something out exit, you haven't control the main loop, then it's a bit strange. Now for shlex, shlex. The shlex module implements a shell-like vector. Now that sounds kind of boring, but the key thing is you can give it a command-line string that you give to a shell, and correctly splits it and read the quotes and deal with quotes and things, and give you back the correct set of list of arguments properly split, so you can feed them to OS and exec. That's very, very handy when you doing lots of commands that come with strings. Yes, the FCMTL module. It's the portal to a very dark world of Unix. I hope you never ever have to use this. FCMTL is a part of the Unix subsystem that you take a file handle and mess around with it in horrible ways. We use it for changing blocking modes. We saw in the PTY module there's a few things that need to be in non-blocking mode, which means you can try and read from it, use it as an error. But it also contains things like leases that don't get used, signals to notify, which is now been since the cert, I believe, creation flags and changes on the pipes. Basically, magic. And now, closing remarks, actually quite long, but first of all, as a young startup, we're meant to be in the best place to adopt fresh technologies, the best of everything, cool web-scale things, they say. That's great, but a lot of them are very young. Reinvent and Zero MQ in particular, and the combination of those two, is still a very young combination. And so things like OS packages are out of date. Even in the latest of Ubuntu, the Reinvent package is too old for us, because it's 2 releases behind. So we had to make our own packages, that kind of stuff. There's still bugs, like I said, there's Slider PG2, there's a bug that just hangs the entire process. We only found one with another company in London had a talk one night, and then, oh yeah, we saw that too with this, it's one of the slider flags. In particular, don't, as you saw in my PTY model, don't reinvent the wheel on optimize prematurely. Yes, it's on the device, influence from every computer science model, it's still good advice. In particular, there are a lot of things that the Linux kernel or system solve for you already. Many of you may not see this. There's a lot of people here who used to do web programming, so happy. Request response cycle, you never see anything again. I used to live in that world, it was lovely. But there's a lot of very key functionality in the kernel. Things like memory management. Don't start writing memory to disk. There are a few caches that used to do that. The kernel is very good at memory management. They can do this job. Caching as well. Kernels already do disk caching for you. Things like sending things to sockets. There's a send file that's very efficient to just redirect from disk out to socket, and that kind of stuff. But on the other hand, you have to reinvent the wheel occasionally. If you don't reinvent the wheel, or at least try and re-implement something, it's very hard to understand the problems that perhaps the original author faced. We've attempted to reinvent several key parts of our infrastructure. In particular, one success story was our load balancer. So we used to run off of HA proxy as a load balancer. We went through, we looked at it, we made a logic information file for it. It was around 4,000 different control statements of ifs and if this hotel was there and that kind of stuff. And it was quite slow. We're like, oh, okay, that's not brilliant. So I sat down, sat down with the vendors, wrote a small, quick thing in about 3 or 4 hours. How'd it go? It's faster. We spent because HFLC runs the recent regexes and we're using a hash table. Then cut down, added more features, and in the end, we're now using that Python 1 library in production because it's both more reliable, because it reloads better, we can modify it more easily, and it's just generally getting slightly faster for us. It won't work again, of course, we have to look at something else again. But it was a very good way for us of seeing the problems there and surprisingly come up with a solution. There are also cases where that hasn't worked so well for us. Databases in particular, we have a lot of fiddling with databases, and discovered in the end that there's a lot of very good reasons why they do what they do. So. And also, Python is really very, very capable. We do a lot of Python development. We have several tens or perhaps 100,000 other code in each generation. And a lot of people claim that Python is too slow for many jobs, but that's really not the case. What we found, for network programming or disk programming, it very much is true that most of your wait time is spent waiting on disk, waiting on I/O. It's not like event does. You can spend up time doing other threads and other processes instead. And so, it's very, very capable. We've done a lot of architecture using it. We're going to keep using it for ages. And in particular, what's looking promising future is PyPy. For those of you who are familiar with PyPy, it's a re-implementation of Python. Technically, it was in Python to start with, but it's now with its own just-in-time compiler that's basically it's very, very fast. So about a year ago, I was at EuroPython, and they were saying, oh yeah, we're only 2 times slower than Python. And now this year, they're like, oh, we're only 4 times slower than C. It's a massive improvement. Generally, on most workloads, we're seeing a 6 to 10%, 6 to 10 times increase in sort of speed. And we can't use it yet because it doesn't support that JIT and also brilliance at once. But there's an interesting work going on making the two combine this summer, I believe. Once that's done, we're really looking to use PyPy for most of the stuff we do. We're very excited by Python moving forwards. It's a very flexible language. And yes, and so that's, I'm sorry, that's most of the talk. I just want to make a few, just say quickly that if you're not going to run, for some reason, a platform as a service, particularly native and nobody else, it's a fun experience. You get to do a lot of playing with different bits of hardware. I've seen a lot of parts of Python I would never have seen in my web decks. There's a lot of very strange parts out there, and a lot of the strange modules that you see in the library index on the side, you never really know what they do. I've seen half of those ones. It's just realising Python isn't just, particularly from the web or from an academic background, it's not just about the one thing. It's nice to get out there and see different parts of Python. Yes, and that's it. Thank you very much. Any questions?
So, any question?
I was wondering if you were considering open sourcing any of your infrastructure.
Yes, so we're considering open sourcing, in particular things like some of the event health libraries we've written a few brilliant compatible libraries, and also things like essentially a load balancer. There's a distributed locking daemon now we have that we're not open source. There's a few things open source. The main problem is extracting them from our internal infrastructure. Things like you saw there, the base daemon, setting queue, that kind of stuff. So we can either make that a separate package and then start depending on that, or extract them properly. We do want to really sort of give that stuff back because there's always something redundant in there that I'll never find because I've written code and I don't see it properly. So I want to make sure that other people see it, try and get feedback, try and get other people using it, and then properly hammer it out as production quality.
Anybody?
So, how your architecture compares to Cloud Foundry?
But it's Cloud
Foundry.
Well, Cloud Foundry?
Yeah.
Oh, right.
Yeah.
I'm not intimately familiar with Cloud Foundry. I've looked at the source code, obviously. In fact, I've given a talk in the same session as the Cloud Foundry guys. As far as I can tell, we're not that dissimilar. There's a lot of similarities, especially with things like message passing, a bit of redundancy, routing, that kind of stuff. Our architecture has changed significantly in the last 3 or 4 months because we can do that when you start something flexible. As far as I can tell, they're very similar. There's obvious differences in the way we handle, like how we run databases versus them. We have a lot more infrastructure for things like monitoring and billing in place than I think Cloud Foundry does at the moment, because that's a big thing for us. So most of our services, most of our runners log their output, they log their runtime, their CPU time, their memory usage, their disk usage, their network layer, all that kind of stuff. And that's kind of a big problem as well. It's logging that stuff sanely in the right place and redundantly is difficult. But yeah, I mean, they're generally quite similar from what I can see, which is reassuring because it means that we'll probably say we're solving a very similar problem, and if the solution is somewhat similar, then that's good.
EuroPython, don't use so much memory from shared environment. EuroPython, pipeline.
Yes. Yes, so memory usage-wise, it can be up to 2 times worse, I believe. But it will also up to 2 times better. Memory usage of PyPy is widely variable, basically based on how much JIT's using, how much code is compiled, that kind of stuff. That's not much of a problem for us because we have very little memory for our daemons compared to the rest of the box. So most of the boxes, they're full of RAM, obviously, we're putting hundreds of things on it. And so most of the RAM is taken up by sub-processors, by Unicorn, by Nginx, all that kind of stuff. And comparatively, our main daemons don't take up much core memory, it's like 20-30 megabytes at most, so that's not really a problem for us. It might be a problem with things like load balancer or the loggers, but we haven't come to that problem. As in, we can't use Python yet, so once we find it, we'll have a look into it, and potentially, from what I've seen, they'll just fix it. You know, they have a very good history of somebody going, that's a problem, and then two days later, it's suddenly all gone, it's better, and like 3 times faster to do it, so we'll see.
Anybody else? Please. Help us.
Hello, I have a two-part question. Are you using ZeroMQ for high availability then?
Yes,
Okay, so I got it right. Then how do you solve if you need to write to a cluster, to a service? Because if you do 2 requests and send it to both, you may end up with one data being different from the other.
So generally,
How do you synchronize it?
so most of our writes like that are, we don't need 100% writing, basically, so we kind of cheat. So we use typically push sockets for all of our logging statistics, which have a rough guarantee of, well, they definitely go to 1 or 0 server for the guarantee. You may lose it if the server accepts the message and then dies, but we can afford to lose a few data points here and there. It's not a very large percentage. In terms of things like Postgres and stuff, that's harder. Postgres, we're using Postgres built-in HA support. But yeah, it's not perfect, and then in networking, nothing ever is.
Another question here.
Did you have a look at OpenStack for handling the lower part of your infrastructure?
We did. The main problem with OpenStack and also virtualization in general was that we saw a lot worse performance on disk layer and also slightly on random memory access. Virtualization layers impact a lot on disk layer because there's no way of routing it sensibly. So virtualization chips and CPUs these days, they route very fast instructions, they're pretty good at memory, but disk layer can't go through direct paths. And so we saw 2 times speed up in real hardware compared to the And we did a lot of disk crunching, we had a lot of swap, we had a lot of apps being loaded in and out at the time, so for that reason, that's why we started to use like real hardware. We do use EC2 and Windows, as I said, for that stuff, but that's much more because people want them rather than we want. It's like customers want to be near their other applications.
You said you were using the PTY module to write to processes. And I guess I was wondering why. And did you have a kind of a crack at pexpect, which we found solved most of our problems?
So I looked at expect and pexpect, and they're not quite, because we do a lot of sort of like raw reasoning writing of chunks of data in and out, they weren't quite what we needed with like a Plex. I mean, our wrapper itself is very close to expect. The reason we're using PTY is mostly because we have a lot of applications, well, a few applications that don't respect things like standout. They try and write identity Y instead. Things like PSQL as well, and command line clients and anything like that, any kind of shell commands, Bash as well. You can do easily run command Bash and you can launch a Bash shell. So for that we have to have PTYs for some support. Yeah, we didn't expect, but we didn't get quite good again. It must have moved. It's a game of try.
Well, that's so, wasn't it?
Hi, I was wondering how many sites can you fit in a gigabyte of memory?
A gigabyte of memory. It depends on the sites. So from our statistics, most Python sites fit down to 64 meg. So about 95 are on 64, about 99% are 128 meg. So in a gigabyte, we could probably fit about 20 or so. We also have a bit of swap in the boxes for obvious reasons. So generally, we like to overcommit the box very slightly. So I'd probably say we pick up 30 in a gigabyte. Only a traditional small website. A big website, obviously, pick up most of the specs.
Hi. you have all these processes and they're targeting these daemons and they're communicating by zero MQ. But what if one of these goes down? I mean, they send this heartbeat, but then one goes down. Do you have any failover or?
Which one goes out? One of the demons? Or
You said you had around 70 demons and processes running and communicating over zero MQ.
and the causes of this, so there's things called the nexi, or nexuses, which are the things that the heartbeats go to. So there's more than one, there's two of those for start. They know what everything is, and then there's two of everything else, is the idea. So when you want to talk to a service or talk to a runner, you ask both nexuses, I want this. One of them responds, because zero Q works. They respond to the list of ones you're active, and then take the list and then ask all of them with zero Q, and one of those responds. So it's very much a case of there's always more than one choice in this given stage. One thing we can solve is if the entire data center goes down, so power outage or fire or whatever. We're working on that, but again, the latency issues I mentioned kind of impact on that. Similar idea would apply.
Anybody else? I actually have one question.
Go ahead.
I suppose we will have an API and an SDK for developers for your platform. And how do you cope with API upgrades and changes? Have you got an API level, just something like a Google App Engine, or it's something like a flowing thing?
So in particular, SDK-wise, we try and be as close to core Python as possible. So there's never an SDK, you just use normal Python modules. So at that level, we're pretty good. We specify a Python version that you want to, and that's about it. In terms of API, we have the version thing, and the IDs have a number. So currently, API is just the same URL for the main site. So in Django, we have a set of class-based views that respond based on what you request. As we upgrade the site, those obviously have to change. But at the moment, we're basically keeping those around, and then when we expand 2 URLs so far, for those who just enter the right status code of HTTP, yeah, eventually we'll have to have a version, but it's not stable yet, so you haven't versioned it.
Thank you. Anything else? Okay. Thank you. Thank you.